Hello ladies and gentlemen, and welcome to another video. My name is Thijs, I'm the Technical Evangelist at Varnish Software, and today we have a very special webinar lined up for you about CI/CD pipeline acceleration. I'll be joined by my colleague Alve, and we'll discuss the concepts of CI/CD pipelines, how they can become slow, what the typical bottlenecks are, and what the solution is. We'll talk about artifact acceleration caching as one potential solution, not only to make your builds a lot faster and scale a lot better, but to make access to developer dependencies a lot faster for developers as well. We have to do a little bit of explanation about the concepts and the potential solution, but in the second part of this webinar, we have a very practical demo lined up for you that features CI/CD pipelines powered by GitHub Actions. We'll talk about a microservice architecture with two apps, one written in Node, one written in Go, that will deploy with Docker images through Helm charts through a Kubernetes cluster. And we'll illustrate a typical slowdown of a CI/CD pipeline and how artifact caching can tackle that. Without any further ado, let's go for it. I'll bring in Alve. Enjoy the webinar. Hi, Alve. Thanks for joining me today.
Thanks for having me.
Well, today we have a lot of exciting stuff going on. We'll talk about how to accelerate a CI/CD pipeline. It's going to be very hands-on, but before we show our demo that we've prepared, we need to cover some basics. What is a CI/CD pipeline? Maybe Alve, you can help our audience with that.
Well, first of all, let's look at what CI/CD means. CI, short for continuous integration. That's the part of your build pipeline where you actually build and test. CD is continuous delivery or continuous deployment, depending on who you ask. And that's the part where you take what you built in the CI part of your pipeline and deploy it on your actual infrastructure. And the two combined make one pipeline that take your code from just that code to something that is actually running and that people can use.
And one of the questions we also need to answer is, what's the effect? So we talk about CI, quality assurance, CD, delivery, but the fact that it's automated really accelerates things. And we're talking about a faster time to live. If you have to do that manually, well, not only can things go wrong because of human error, but it'll take a lot more time. And another use case that I found really interesting is in organizations that have increasingly more services. I'm going to throw in the buzzword microservices. You really need this CI/CD pipeline for a developer to see the end result of their changes sometimes. Sometimes setups are so complicated that you need a CI/CD pipeline to actually get it done when there's a lot of moving parts. Which brings us to the next bit. The crucial bit is, why would you need acceleration? You hear a lot of organizations struggling to keep their builds fast, which if they're not fast, it prevents them from going live. You talked about the developer as well. But why would that happen? I would assume, you just said it, introducing more developers on the platform adds this level of pressure?
Yes.
Is it just that?
So there are a couple of things that will contribute to CI/CD pipeline slowing down. Of course, there are resources on the machines running those CI/CD pipelines that will have something to say. That is always something you can sort of scale up. You can always add more capacity there. But there is a side effect of increasing the amount of CI/CD pipelines. And we're seeing this more and more, that the dependencies on the CI/CD pipeline, those artifacts, those Docker images, Helm charts, NPM modules, all those things that a CI/CD pipeline will pull in during its runtime, that is actually things that usually will have to come from outside of wherever this CI/CD pipeline is running. And we're seeing that increased reliance on CI/CD pipelines is causing slowdowns because the artifact repositories become bottlenecks.
We can conclude that it's not just compiling your software that takes time, but it's those overloaded repositories. And maybe we should name drop some of them. We
Yes.
talk about artifacts and repositories. What type of repositories do we have?
So there are many different flavors, but the usual suspects are JFrog Artifactory, Nexus from Sonatype. We have CloudForge, Harbor, Quay. Even Docker Hub is quite aggressive in its rate limits. So we see pipelines being slowed down both by those private repositories that you pay a lot for being able to have a sort of a universal repository manager, but also from the public open repositories such as Docker Hub. They both will have different ways of slowing down, but the end result is that the CI/CD pipeline just takes a whole lot longer.
That's an interesting take, seeing it from those two angles. Like typically when you do something self-hosted, which is definitely possible with some of the names you've dropped there, then it's a matter of infrastructure, it's having enough resources, CPU, RAM, but also network. That bandwidth needs to be good. But then when you talk about these global platforms that sell it as a product, that's where rate limiting kicks in. So how do you accelerate that? Well, a lot of people just throw servers at the problem, which is a way of handling it, but it's not really cost effective. And we have this punchline, this quote that we use on our website. It's a marketing term: scale performance, not infrastructure. And it actually makes sense. And we'll get to the demo real quick here, where we'll show that instead of just scaling out your infrastructure horizontally and vertically and spending money on it, but also licenses, because some of these you need to grow your license and spend maybe sometimes even thousands, maybe tens of thousands of dollars more on making that scale. So we have a way of using caching. And I'd like you to talk a bit about caching, because a lot of people say, oh, caching, we'll use a CDN. What's your take on this, Alve?
So that's a great question. And this really gets to the heart of the differences between sort of this use case and many use cases that people will be familiar with from the traditional web and API space. So if you have a web server that's serving a web page, it is basically a foregone conclusion that you are going to put that web server behind some form of CDN. That just makes sense from a web and API point of view. And a CDN is just a big distributed cache. The CDN has points of presences roughly concentrated, in accordance to population centers in the world.
And I have to mention this, I feel forced to mention this. Caching these types of workloads is our origin use case.
Yes.
As Varnish Software. There's no way around this. This is how we started, and this is still a very big part of our organization and our business. However, as the internet evolves, because that's something we haven't mentioned yet, all these artifacts, all these parts of the build pipelines, they communicate over HTTP. We are an HTTP cache. And as it happens, we see a lot of clients, a lot of prospects coming in with the question, can you cache this?
Yeah. And really the big difference between the traditional CDN use case and this CI/CD worker, Docker pull kind of use case, they both run on the same protocol. It's both HTTP, but it's really a difference in the clients, how they behave and where they're located, and the number of them. Because in a CI/CD environment, you have way fewer clients, and they are hyper localized to maybe just one geographic location, one data center, even just one rack, one Kubernetes cluster, right? So they're really tightly packed. You know exactly where they're going to be because you put them there yourself. And then compare that to if you're a big video streaming platform, your clients are going to be all over the place. So that's one big difference, and that's one of the reasons why the traditional CDN approach doesn't work well here. Because
So that means you need to put a cache exactly where you need it.
Exactly. You can,
and that doesn't mean it's a single cache. It could be a distribution where you need them. So you talked about these different Kubernetes clusters you have, the deployment targets, getting them as close as possible. Maybe even within your Kubernetes cluster is a good approach. On the other end of the spectrum, you have distributed development teams that are globally. Maybe for them, the traditional CDN would work, or if you have specific offices where these people are located, then maybe a local cache there would make all the difference. And as a matter of fact, we actually built a product to do that. And we're going to showcase it in the demo. And since you are involved in the development of it, I'd like you to talk about this artifact cache solution that we have set up and built and that we are eager to show to you.
Yes. So we built the artifact cache to cache artifacts. Simple as that.
Again, remind the audience what is an artifact, because it's a bit of an umbrella term for a lot of things.
It's definitely an umbrella term, but it's becoming sort of the standard term to describe these things. It can be a Docker image, npm module, Python package, NuGet. It can be, Helm chart. Just look at the list of packages that is supported by these universal repository managers. It's quite a long list. Every single programming language almost has its own package manager of sorts.
And you happen to have built a solution to make that a lot faster.
Yeah, and that really gets to the heart of it. You use these artifacts throughout your CI/CD pipeline. At the very start, you'll be pulling in Docker images and Helm charts. You will pulling in dependencies to build your software in that build step. You might even use some during the testing step. And then when it comes to, you produce your artifacts and you push them to the artifact repositories. Now you're in the CD part of your pipeline, and your CD software is pulling in, again, those same Docker images you just built. It's pulling in Helm charts, it's pulling in different things to deploy on your architecture. So we're producing and consuming artifacts, and that's really, that's a lot of data. Docker images especially get quite big, and that's why we think that having a artifact cache in place as close to your workload as possible, typically within the cluster, makes just all the difference. It really can shorten build and run times, and just shorten the length of that CI/CD pipeline very significantly.
Yeah, I've seen examples where we 5x it on these little setups that we've built, like these demo setups that aren't that powerful. You could 5x your performance, which is a bit of a statement, but yeah, it depends on how much pressure ends up on there. Now, of course, we are Varnish Software, and this artifact caching solution is powered by Varnish Enterprise. So maybe talk us through how you've built it and the details you feel comfortable sharing about how it works.
Of course. So we've taken Varnish Enterprise, which is our caching engine that we build and develop, and we've applied a set of rules on top of that caching engine to turn it into a Docker aware, a npm aware, a Go aware artifact cache. And we built quite a bit of custom logic into this. We do things like, and this is quite important, we do access control integration with the origins. Typically, if you can just put a caching proxy in front of a private repository, now you've just made that repository public. You need an integration between your cache and your origin in order to maintain that access control.
And there's a hidden danger behind that, because one could say, oh, we'll respect access controls. And that means for every single user, you have a separate cache. Let's say a Docker image that has like 5 layers. Well, you have 5 layers per user, which pretty much takes away the power of that, right?
Yeah.
So you factor that in, I'm assuming.
Absolutely. So Docker image is a good example. Essentially, what we'll do is when we detect that the incoming request is coming from a Docker client, we will go ahead and ask the origin whether or not that client with its authorization has access to that image. And the origin, if the origin says no, that client does not have access, then we'll go ahead and deny them access, just like if they were to pull it directly from the artifact repository itself. But if they do, we will actually remember that. And all the subsequent operations to pull each of those layers for that Docker image, that will be pulled from the shared Docker cache. So we cache each layer. We cache each layer across images, and we make sure that each and every client is authorized before they get any of those images. So really, we what we've done is we've implemented a seamless access control integration. Zero configuration required. You don't need to point Varnish at any of your access control software. Varnish doesn't need to know about that because we rely on the origins access control.
The marketing term for that is pre-flight authorization request.
Yes.
That's the one we like to use for that. But it's a very powerful aspect. And you've mentioned this really interesting detail about the Docker images. So one could say on an artifact level, yes, we store the shared artifact so that everyone can use them who has access, and we enforce access control. But even at the layer level, we share them. So let's say you've built a custom image like we'll do in the demo, which is highly anticipated. Yes, we'll go into the demo as quickly as possible, where we maybe rely on an Ubuntu layer. Well, that Ubuntu layer, if it's used by other private images, it will be shared. So it only has to be cached once. So it's not on a per artifact basis, it's on a per layer basis. And that makes it super efficient.
Yes.
And that could save like hundreds of megabytes, even gigabytes of traffic over the wire.
Yeah. And especially since Docker lends itself so well to this type of caching, because the base images, they typically stay the same across all your images, and even when you push new versions of your application, that is pushed on top of those base layers. And the further you go in a layer stack in a Docker image, typically the less frequent those layers change, and the bigger they get. So you get sort of a double benefit when you cache Docker images like this. And don't forget, Varnish as a reverse proxy able to cache any kind of HTTP request has a very different set of constraints compared to a web server database combo. The fact that Varnish is a cache allows us to scale in a very different way to the origin, where origin needs to deal with replication and keeping a single source of truth across many different origin servers. Varnish can just scale as the caching layer in front. So when you saturate the network card of one Varnish, you can just add another one and point that to the same origin or cluster Varnish if that's what you want. And that's how you sort of scale that caching layer to be able to handle much more traffic than you would be able to with a sort of a proper origin web server.
Well, and you've built this out as a product because we've been talking about Varnish itself, but a lot of the complexities and the configurations and all the things you need to do to make it perform and scale well are hidden behind a nice layer. So if you're planning to use that type of solution, it's as simple as registering your package type and the appropriate origin, which makes it kind of interesting because you have this abstraction layer, a shield in front of it that not only performs really well and scales really well, but it allows you to plug in and plug out. Like, oh, you're using Nexus, for example, as your Docker backend. Well, then you decide to switch it up and use Artifactory instead, and you don't have to make a lot of changes. It's simply changing for the Docker artifact type, changing the backend.
Yeah.
Changing the URL, reload Varnish, good to go. So
yeah.
It's actually a solution, not just a toolbox.
Yeah, and using one of those universal repository managers makes it super easy for the Varnish configuration. You can just point Varnish at Artifactory and it'll just work, right? That's a single line configuration. But Varnish also makes it really easy to say that, okay, I want all my Docker images to come from Docker Hub, let's say, and all my npm packages should come from npm.js registry. So Varnish can also act as this sort of single unified delivery layer where it takes all kinds of different requests for different types of artifacts and finds the right origins to pull into the cache.
And this abstraction layer is not just the benefits as such. We have configured our demo, or we'll go through the motions and end up in a situation where even the public images that are readily available online can be cached within our system, because it wouldn't be the first time that a build fails because there might be an outage somewhere, and you don't want to take those risks. You want to keep even those public shared artifacts as close as possible.
Yes.
And even if it's on the Docker Hub or npm.js, cache them locally. This is also a feature of a lot of these repository managers, but we do it at scale.
Yeah, and get under those rate limits.
Yes, stay under the rate limits. And by doing so and by implementing that solution, there's a couple of things that happen. And of course, faster builds is what a lot of organizations are chasing. And doing this, of course, at a relatively affordable rate. Faster dependency pulls, both for the build pipelines, so those CI workers you've been comparing to the users, but also to the developers back home or back in the office. When they do Docker pulls at scale or npm installs at scale, those will go a lot faster. In our demo, you'll see that we have 2 Varnish caches, one in cluster on the Kubernetes server to ensure that the builds go fast and the deployments go fast, but also one that is hosted separately closer to where the developers are. So when they do a Docker pull, it goes fast.
Yeah.
But I'd like you before, as a sort of a closing note of this intro section, to make sort of a side-by-side comparison of these 2 goals we have. Do it faster and do it cheaper.
Well, I think they are, 2 facets of the same solution. When you accelerate these workflows, it means that your developers, well-paid developers, will be able to do more work. It increases efficiency. It reduces the developer friction that really, really kill your flow as a developer. It means that you can produce more faster with fewer people. Across a big organization, that really, really adds up in terms of the developer hours, developer days, developer years spent. And of course, we do have to mention the reduced egress costs. If you have localized caching inside your cluster, inside your data center, that can also really reduce the bill at the end of the month or at the end of the year for some of these cloud platforms that do take quite a bit of...
and not just the cloud platform, but some of these repository managers have a SaaS/cloud offering where they bill you for the traffic as well. So you pay your license fee, and on top of that, and we've experienced that in our tests, that it adds up quite rapidly. Even if you buy the cheapest license they have, if you start pulling gigabytes through, and it's not that hard because pulling in those Docker images will take a couple of 100 megabytes for a single pull, then the bill starts adding up real fast. So you've convinced us about that. It's egress, it's also infrastructure, it's licensing. But on the other hand, there's organizations whose sole focus is to do it faster. And I think now is the appropriate time to put in the legendary XKCD image of compiling. Remember that one, Alve?
Yes, where they're like fencing on the chairs. Yeah.
Fencing on the chairs. We'll put that in right here, right now, because that's super appropriate.
Yeah.
Which brings us to the end of this value proposition part. If you're still here, dear audience member, it means you're interested. So I think it's time to show the demo. We've built the demo because we can do all the talking we want, but the best way to convey the message is by showing it. So Alve and I have been working on a demo setup with a CI/CD pipeline and an application. Deploying a single monolith application is not the way to go here to illustrate some of the complexities. A lot of organizations have a lot of microservices. We try to keep things tangible and chose to have 2 of those. So here's my Visual Studio Code and the app. Well, there's 2 apps, a Go app. We deliberately wanted to write in 2 different languages. This is an API, a to-do list API written in Go that can be consumed. And there's a little bit of storage, but all that storage is in memory. Now, of course, we have a second app, which is written in Node.js. It's our front-end app, and it connects to that API. But there's all the front-end logic. You see a bunch of HTML happening, and then some controller actions. There's a little bit of an MVC framework allowing you to wrap around that API, and you have to set that through the API environment variable. That's the way you define the endpoint of our 2 apps. So we have those apps in play, and then, of course, we need to launch them. If you're a developer, well, you can do a Go build and build the API. It's pretty fast. And for the front end, you do npm install, and you have those 2 applications. And you'll run them, set the port environment variable, listens on port 8080. And on the other one, you'll do the same, but you'll also specify an API endpoint. And then you can click the link on your local host, and you can actually see how the app works. This is our little to-do list app that we're going to build and we're going to deploy ultimately in the cloud on a Kubernetes environment. For now, as a local developer, you can play around with it. And it works. You can add items to a list. You can delete items. Now, of course, you want to package that. you're not going to run these individual on a server. If we're planning to release this to a Kubernetes cluster, you need to package that into Docker images. No problem, we've got you covered here. So if you run these apps locally, you can also build them into Docker images. You do a Docker build, and we pull in the dependencies from our docker.artifactcache.com. That's our Nexus repository that we're proxying all the layers through. We're building the local image, and we have it here. These are the images. Then we can push them directly. We can push the updates to our Nexus repository. That was the Docker part. You have a little bit of a Kubernetes part as well, where you can use the Helm charts that we have locally to run these Docker containers. When you check helm.list, you can see that we have the to-do and the to-do API launched here locally. They're deployed. And then you can run kubectl, get all on your local Kubernetes cluster, and you can see that these things are running. But really, we want to use a CI/CD pipeline to build both of these projects, package them both into Docker containers, orchestrate them both using Helm charts. And then ultimately, you, Alve, right, have an ArgoCD system in the back that listens to those Git changes.
Yes.
And to those Helm changes to pull those in.
Yeah.
All right. It's CI time, ladies and gentlemen. So yes, you have the Node app. Yes, you have the Go app. You've seen how we deploy and package them locally, but you also have a workflows folder in the GitHub folder. And that build.yaml file is actually a definition in YAML format of how to orchestrate all that in a CI/CD pipeline. It listens to certain branches, in this case, the main branch, and it has a set of jobs. It has 4 jobs to be specific. Build API is the first one you see, and that actually takes the Go code, gets in the dependencies, and does a build. And then you have Helm API that takes that Docker image as output and makes a Helm chart out of it. So you see all these different bits and pieces like build API. You also see how we pull in the Go dependencies through our Nexus. You also see how we build it. You can see how we actually proxy all the external dependencies through our artifacts. And then we actually build the Docker image, as you've seen before, done manually. And when that's done, we can push it to the artifact repository. And then with Helm API, we depend on the build API step to be successfully processed. And then we package the Helm chart. We do some find and replace, and we push the Helm chart again to our artifact repository, which is Sonatype Nexus. The same actions happen for the build front end. The front end does it based on npm, and we also proxy those packages through. So you actually go to npm proxy artifactcache.com and it will pull it from Nexus. But then it's time again to package that in Docker. So again, we manage to pull it in from docker.artifactcache.com, which is our Nexus. And that allows us to build our image, get the dependencies like the Ubuntu or the Node images, get it from our artifact cache, and then ultimately also push it to Nexus. And the same step, the final step, is also taking that image, orchestrating it, building a Helm chart, and pushing that Helm chart to our artifact cache. So it already is quite apparent that there's a bunch of dependencies being pulled in. What does that look like when that actually is being picked up by GitHub Actions? Before we continue, Alve, maybe you should chime in here. Why did we choose GitHub Actions?
So GitHub Actions really is becoming the industry standard, I would say. More and more companies and developers are choosing GitHub Actions. It's becoming sort of a very universal thing, whether you're using it through GitHub or something self-hosted like Gitea, for example. One of the things that GitHub Actions allows you to do is, yes, you can run it on their hosted platform. It'll run there in its own little environment. What you can do is we can set up a self-hosted GitHub Actions runner. And to me, that is pretty key, because then you're actually running your CI/CD pipelines yourself in your own environment, close to where your code actually lives, close to where your artifacts lives, and you can run it on your own hardware.
And we'll go through that. These are steps that we'll take throughout the demo. We'll start here. This first version you see is using the GitHub runners that are hosted on GitHub's platform. But ultimately, we will evolve into having local runners, which Alve explained with all the benefits. And then the key benefit in the end, we're already spoiling it a bit, is that you can have a Varnish container running within the same cluster, and you don't even need to go outside of the cluster to get those dependencies. And that's truly powerful. All right, let's see how this push behaves. Version bump new build is the name of the commit. I wasn't really that inspired when I did it, but you can see that it is running. Let's have a look at the build API step. So there's 4 steps. Build API will build the Go program package into Docker, as you can see here. And when that's done, it will push the image containing our API backend to Nexus, which is happening right now. It pushes the image, and as soon as that's done, there'll be some teardown logic. You can also notice that now the dependency is fulfilled, and we can take that image and process the Helm chart. It takes in the Helm dependencies, pushes the Helm chart, and some post actions. If we look at the summary, the first service is fully packaged. Of course, we'll fast forward a bit because we don't want you to sit through an entire build, but you can see that the front end works, the Helm works as well. And ultimately, it took 1 minute and 53 seconds to get that processed. Here's our built front end that we did earlier. What takes the longest? Of course, building the Docker image and pulling in the base images and then pushing it to Nexus. So that's pretty much where we're at right now. We've done a successful build, but there wasn't a lot of pressure on the system. So that meant everything went relatively fast. One element that I also wanted to show you is how tightly integrated our Nexus system is here. So just as a quick reminder, Nexus is the artifact management tool that we've chosen that uses or that supports Docker images and NPM and Go and all these different kinds of artifacts. Maybe Alve, you can elaborate why we chose to use Sonatype Nexus and not JFrog Artifactory for this demo. We could have, but we did.
Yeah. So I mean, the 2 repository managers are quite close in terms of feature set. For us, it really came down to Nexus having a easy to get a hold of self-hosted version. So you can download the community edition of Nexus, run it on your own hardware. That really allowed us to sort of control the environment, because we're going to, in a bit, try do some stress testing and getting that repeatable slowdown in Nexus will then allow us to show how much the caching can really accelerate things.
Absolutely, because if we were to do this on JFrog Artifactory's SaaS cloud hosted platform, it probably would have worked, but our bill would have been much higher because they bill us per gigabyte. And for this sort of smaller environment and with the limited traffic we can generate, it was easier to overload Nexus. And if you look here at how we're pulling in those resources, you can see that we're actually logging in to docker.artifactcache.com. So artifactcache.com is our own domain, and we created a Docker repository hosted on that Nexus server. And that's the one we'll overload in a second. So you can see that there's already references to it throughout, for NPM, for Go, for Docker, and even for Helm. So that is the package repository we use. But remember, it's easily interchangeable. We're not, because we chose Nexus doesn't mean we don't like JFrog Artifactory. It's pretty much the choice you make makes it entirely compatible. Because remember, it's all HTTP. And then you may ask yourself, what does that look like? Well, here's an overview of our Nexus Community Edition that we have. Also hosted on a system, on a server. We have different host names for it. So the host name with which we access it is nexus.artifactcache.com, but docker.artifactcache.com, npm proxy, go proxy, they all point here. And you can define that. Here's our Docker proxy. It has Node and Ubuntu. As we've mentioned before, we host them here, despite them being public images, because let's say there's some outage of some sorts or some extra latency, well, we're not subject to that because we have those versions cached. You can also take a look at our Docker repo that has our API here to do API and to do like everything's there with the manifest and the tags and all the blobs. That's where we'll pull some of the stuff from. But another element we haven't talked about is that there's other parties involved. Yes, there's CI workers running these things, and that needs to be fast, and they'll be accessing these repos, but you also have developers doing it. So when you are a developer on your computer, you might do a Docker pull from that repository, which also causes a little bit of stress. There's bandwidth consumed, of course, hundreds of megabytes to do that, but yeah, that's also relatively CPU intensive when you do that at a certain scale. If you have a team of 20 developers and they start pulling in all these types of resources for the different microservices they're working on, well, that could cause a little bit of a spike on the system. But for now, all is good. It all works pretty well. As you can see, we're pulling in those images. So there's not really that big of a problem. Look, we're even doing an npm install here from the npm proxy artifact cache, and everything works. Now let's switch gears. We're in a state of harmony. Life is good. Things work well. But it isn't always the case. And as Alve explained earlier, if you're an organization that has many deployment targets, many CI agents running, or developers also that do their pulls at the same time, there might be a lot of pressure. Now, let's not beat around the bush. Alve and I don't have the horsepower on our laptop to pull down that system using regular Docker pulls. And Alve already hinted that we would do some sort of stress tests. And we chose K6 for that. And we have some K6 scripts. K6 is an open source load testing tool developed by the people at Grafana Labs. And I actually like it because they offer a JavaScript interface. So what we have done, and it's based on a lot of the research that Alve has done, is we've turned a typical Docker pull, we dissected that, and made it into the underlying HTTP calls. Alve, can you highlight what actually happens behind the scenes?
Yeah, so we can break a Docker pull into roughly 3 parts. The very first part is the sort of the authorization check. The Docker client will check, do I need to authorize to access this repository? And if not, then all good, we can go to the next step. If not, there's a whole little dance to get a token for the subsequent accesses to that Docker repository. The second step is getting the manifest, because as you just saw, when Thijs pulled the Docker image, it had a bunch of progress bars, all progressing at the same time. Each of those are layers in the Docker image, but for my Docker client to actually discover those layers, we need the manifest. Docker registry will say, okay, here's my layers for this image. And then we get to the third step, and that's where really the magic happens for us. That's when those progress bars start appearing. That's when your Docker client will then pull in each of those Docker layers. It'll be pulled in by referencing the hash of each layer. And that's pretty key. The layers are content addressable, meaning that they are referenced by a hash of their contents. And that means that we can just take that hash and create a cache key based on that. And then we are really good to cache it for an indefinite amount of time.
And we've actually mimicked those actions, like those 3 actions, into this script. So let me walk you through it. So we're going to the Docker repo hosted on our Nexus server, and we're pulling in our 2 private images for, of course, the front end and our API backend, as well as the public ones they depend on. Those dependencies are also layers within those private images, being Node for Node.js, being used by our front end, and Ubuntu, which is the base image. Now, of course, I randomized them a bit because I don't want to pull them in sequence. I want to have a level of randomization when images are pulled in. Now, of course, we're getting the latest tag of them. So every time we do a push, we get that latest version. But remember, authorization is key here because this is strictly private data. So we need to set an authorization header. Since we're using the community version of Sonatype Nexus, we don't really have tokens, so we rely on basic authorization. So we have a username and a password, which you can inject using environment variables. And then we set some accept headers and a host header. And then, of course, we need to define the scenario. And the scenario initially is that we'll do one user, one virtual user, so no real concurrency, and it will do 4 iterations. What are these iterations? Well, going through the 4 different images. We can then set that to a much higher number if we want to, and then actually go through the 4 images at maybe 50 users. And remember, 50 is already quite a bit. If you know that it's a couple of 100 megabytes per user, you can kind of estimate that we're going into gigabytes here. But that's a stress test. And then you take the image, you get the manifest URL that Alve talked about, which is in a set format. As you can see here, it takes the image, manifests, and the tags. And the result that comes out of it, we'll expect. We can do some debugging and check that the status is 200. But the output is actually in JSON format. So we take the result, do a JSON decode, and check if there's a layers property. And if that is the case, well, then we can just take those layers and iterate over them, over the different layers, possibly follow redirects, and then get the layer digest. And the digest is that addressable content that Alve referred to. So you get the result, you do some debugging, and then you sleep in between. And that's pretty much how we cycle over an individual image with the different layers and the manifest, but we do that 4 times. We do that for each of these images. We also did one for NPM. It has a similar protocol, right? Alve, it has a manifest. These are public images, Express and Axios. We also do authorization, and since this is hosted on the same repo platform, we don't need specific users or passwords. This is all centrally managed in Nexus. And the same 50 users, single iteration in this case, because this is all happening in one iteration. You get the metadata, which also is some kind of manifests. And then there will be a tarball URL because it uses tar compression, tar GZ compression. And you just iterate over all those layers and you pull them in. And if there's other underlying dependencies, which are entirely possible, you pull those in as well with a second of sleep. So not only are we replicating Docker pulls, we're also taking npm's installs and putting some pressure on there. Now, a little bit of a spoiler here. It's primarily the Docker pulls that are going to kill the system.
Yes.
So let's start by running this locally on my own computer. I'm based in Belgium. The infrastructure is hosted on Amazon in their data center in Frankfurt, and it's pulling that in. There's a little bit of a distance here. We're taking it in from the proxy, and it comes in at a decent rate. We only have one virtual user doing this. And let me fast forward it a bit because you don't really want to sit through this. It'll take about 40 seconds, I guess. So what do we learn from the output? Well, we see that all is green. So we've pulled in all the manifests. We pulled in all the blobs. And that was already 931 megabytes of data. It took about, on average, a second for an individual HTTP request. And remember, all these things you're seeing are all HTTP requests. But the entire iteration, so pulling in a single Docker image, takes on average 9.99, let's say 10 seconds. And it took about 40 seconds in total to get all of that true. So that's that. But of course, that is for me being an individual developer sitting at home pulling it in. We have to do the same thing closer. So I set up a server in the same data center on AWS in Frankfurt that has K6 installed. It's a reasonably beefy server. It has to have enough network, enough CPUs, and enough memory to do this. So let's run it again, but a little bit closer now. We're in the same data center. And as you can see, it goes much faster. The physical distance is a lot closer. There's a lot less network latency. And we did it in 7 seconds instead of 40 seconds. And the average HTTP request duration is now 100 milliseconds, which is blazing fast. And a single iteration took about 1.8 seconds. But again, 931 megabytes, 7 seconds. So distance does matter. But when you put those under pressure, like Alve indicated, hyperlocalization is key. You want things to be as close as possible. Now let's scale it. Let's cause some trouble here. Let's scale this up to 20 users, which isn't that crazy, right? You can have 20 developers sitting around. And when you start doing that, I'm not going to make you sit through it. Let's fast forward. Look, we're already 40, 50, a minute. It took 1 minute and 26 for the same thing. And a single iteration now takes 20 seconds. So with 20 users, you can already put a decent amount of pressure on there. Mind you, that thing we did for 20 users was 19 gigabytes. So if you were to pay for the data traffic in terms of egress or as part of your maybe JFrog subscription, that would already cost you. And let's do that side by side. We're pulling in NPM packages. And that went reasonably quick, right? An iteration took 2 seconds. When we start adding pressure on the system, because all of these Docker pulls, that will be slow. Let's say you're a developer sitting at home, you want to do that again. If I fast forward, you'll see that it took 35 seconds to do the same job. And let's do a similar comparison with Docker images. When I add the time command in front of the Docker pull, we can measure how long this Docker pull takes. And it takes about 4.4 seconds in total, which is reasonably fast. Now let's add some pressure on the system and try that again. The same type of pressure we did for the node images. So as that happens, we're going to do the same Docker pull, add the time command in front of it again, and see what's going on. Of course, I'll fast forward it for you, and we can come to the conclusion that this run under pressure took 54 seconds instead of 4 seconds. So we're clearly in trouble and we're in need of acceleration. But that's just from the developer perspective, pulling it in remotely. What happens locally? Our GitHub Actions might also slow down. So when the system is under that much pressure and we're building it again, it is going to take a lot more time. First to build the image, because in order to build the image, you need the Ubuntu image. And in the build front end, you'll need the node image. And the repository that we're relying on is already under a ton of pressure. I'm going to fast forward it again. Look, it takes 2 minutes for that one step. Pushing it will take time. I mean, it's adding up. If we look at the end result, when the system is under pressure because 20 people are pulling in data while we're doing a build, it takes 10 minutes, which is way longer than the, what, Alva, 2 minutes that we had earlier?
Yeah, just under 2 minutes.
So we need to do something about that. And that's where our solution is going to kick in. Now, I'd like you to elaborate, Alva, on the local runners and what impact they will have. Can you elaborate how you configured them and where they're running?
Yes, what we've done is we've set up a Kubernetes cluster. And on that Kubernetes cluster, we've deployed a actions runner controller and a actions runner scale set. This is something that's provided by GitHub. You configure it, have it register with your registry with the appropriate token. And as you can see there, Thijs is showing the actions runner set and all the individual runners. Because this is a self-hosted solution that can scale up. It can, scale really to any number of runners that can execute at once. But you do run into limitations on the network side and on the CPU side, especially.
Because remember, you're hosting this on your own resources. It's not like in GitHub, they present it as a service and they have a near infinite amount of infrastructure, really good network. So it does require some thought. But if we, and let's do that, let's push in, let's make some changes to our build.yaml and start leveraging that. So when you look at our build.yaml, we're relying on Ubuntu latest, which is a hosted version on GitHub. We can change the runs on and choose actions runner set, which is the name of the runner set that Alve chose, and that recycle that for every part of the build step. So building the API, building the Helm charts for the API, building the front end, and doing the same thing when you are building the Helm charts for the front end. And that's pretty much it. So now we've set where we want to run it. And that name of the action runner set is known in the system. So then it's just a matter of pushing that commit through. We'll call this commit local runner. As soon as that commit is pushed and picked up by GitHub, it knows what type of local runners were registered and it will start using them. So when you go to your runners here, which is part of your settings, you can see they're all idling now because there's not a lot happening. But as soon as that push is being received, you'll see that some of these are active. We can actually click on one of those action runners and see that this one is responsible for handling the build/build API job, which is quite convenient. So now all of that is running locally on the cluster. But Alve, that will give us a little bit of an advantage. But since our Nexus server is not hosted within that cluster, it's in a central location, well, we need to change other things, right? So how would you approach making that a lot faster and leveraging Varnish, specifically for the builds?
Right. So since we have our own self-hosted runners on our own Kubernetes cluster, it's really not a big deal just to put Varnish into that same cluster. We put in Varnish as a service running on the same Kubernetes cluster, and then we'll have to make some edits to that build.yaml.
Which we'll do now.
Yes.
Oh, here we go.
So basically take all the places where we previously pointed directly at the Nexus instance, and we point it at the artifact cache running inside that Kubernetes cluster instead.
And it starts with finding a place where you can fetch those Go dependencies. This is important, right? This is not a publicly addressable repo, right? So maybe you should point out why that is so significant in terms of performance and scalability.
Yes, so we're using the service name for Varnish here, but we're using this local service name really for the performance, because that allows us to go through the least number of networking layers inside Kubernetes. This is really something that I think is worth doing, making sure that you're not hitting a bottleneck by getting too far out of your Kubernetes cluster. And this is also why it's so crucial to have that artifact cache inside the cluster, because there really is a big difference between pulling between services running on the same cluster and going to an external service, especially for those higher throughputs.
And to add on that, that's why also so crucial to have your GitHub Actions runners locally, because otherwise they wouldn't be able to access that endpoint. GitHub, the hosted version, couldn't access a svc.cluster.local URL. And we've done it now for Go, but as we go through the motions, of course, we'll change the Go proxy and all the Go related parts, but it also applies to Docker. So those public images like Ubuntu and Node, well, we can proxy them through Varnish as well. And when we actually build our own private images, both for our front end and our back end, we can now prefix those images with the name of our cluster and actually push to them. And you can see the AI of our IDE is already suggesting what we were supposed to do. So we're now pushing through Varnish, but Varnish is not a database, not a source of truth. So Varnish will be clever and notice that these are likely post and put calls and immediately send them to Nexus. So you have a single point to push, but that's also the point where you'll pull. And that's where also a lot of the value comes from. And we'll do it for the front end too. Where do we want to get our node dependencies? Well, those public dependencies will also proxy them through Varnish, as you would expect. And when you do an npm install, the registry that you refer to is also that one. And then, of course, we repeat ourselves by also changing the location where we fetch the public Docker image and where we will push them. So let's run that again. We'll rerun those jobs that were successful ones. And now we're pushing everything to Varnish on the local runners. Let me fast forward that again for you. All the actions are taking place. Go is being set up. Docker images are being pulled in and built. And ultimately, they are pushed to Nexus. And the post teardown steps are happening. As the build API is built successful here on our local runner, the Helm API action kicks in, and it will take that image and will build a nice Helm chart and push it. Same happens for the front end, as you'll expect. And when we take it down to the wire where we see the numbers, it took 2 minutes and 10 seconds while being under pressure. I mean, we are sending a lot of traffic on that system through Docker pulls. We're simulating a lot of builds happening at the same time. And still, Varnish remains unfazed and can easily handle that within that reasonable time frame of 2 minutes and 10 seconds.
Yeah, and I think it bears mentioning that this is the strength of using a proxy in front of your web server. You know, that is a tried and true architectural stack, and it comes into play here as well. Since the proxy has a whole different set of constraints, and especially for this workload, we can essentially scale up to basically saturate the networking you have to your machines. So that's typically the bottleneck we see for workloads that do a lot of Docker pulls, for example. They are super cache friendly and also very easy to serve with minimal CPU resources.
And you can see as all of this is happening and as all those builds start taking place, the cache hits are going up. We're looking at Varnish stat, which is a statistics tool of that Varnish server. And as the builds come in, those cache hits and requests will go up. Of course, we need to position we need to explain how these caches are positioned. This is the in-cluster cache that is only used by those build tasks. Our developers who are still remote will use another Varnish, and we'll do some DNS changes for that. So when you check the host name or the IP address rather for the host name dockerartifact.cache.com, you have this one. But of course, I want to change that now. I have a separate server hosted somewhere closer to where in this hypothetical use case, we have a developer office. So we'll change the DNS record to another value, as you can see, to 212, and that's our Varnish node. That's a different Varnish node, not the in-cluster one, but the one hosted closer to the office. And then when you start running that again, those scenarios at large scale, you can see that these iterations are actually quite fine. And when you run them directly to Varnish on the internal network, if you want, because these AWS nodes have an external network interface and an internal network interface, when we decide to run it within that network, it goes even faster. Look, it's 3 seconds 98. It's 300 milliseconds total duration time. And we've pulled everything in 16 seconds at a rate of more than a gigabyte, not a gigabit, a gigabyte per second. So we're performing pretty well, I'd say. But when you then run this at the scale you want and you check how Varnish is behaving, here's the proof. We're easily processing up to 10 gigabits per second. And you can see the requests coming in. I mean, Varnish is unfazed. In terms of resources, it really has no problems. And all those requests come in at massive scale. And this is a small setup that Alve and I have built. This is 10 gigabits per second, which brings us to the final stage here. I mean, the CI step is all fun and games, but one of the primary targets we have is to accelerate deployments as well. Now I'd like you to step in, Alve, and show part of that CD system.
All right, so I'm here in my editor, looking at the front-end JavaScript application. It's called todo.js. It's a pretty simple application. And I'm just going to make a sample change here. So I'm going to change just the header here in the HTML itself. Say we want to create a new awesome to-do list, if I can spell right. There we go. And I've also gone ahead and pre-made a change to the chart version and to the version we want to deploy to our ArgoCD cluster. Because a big part of the GitOps philosophy is that your deployment should match whatever is in the Git repository. So we have our changes ready. We write a nice commit message. We will go ahead and just push it, send it, and there we go. We have now sent our commit to our Git repository. And from there, we will go into GitHub and see the action in progress.
Now, before you go to GitHub, Alve, can you show the existing application?
There we go. So right now, our app says create a new to-do list. And remember, we changed it to a new awesome to-do list. So ideally, once the CI/CD pipeline finishes, we should see this update.
Now we have the CI part on the one hand, which we've shown extensively.
Yeah.
That is being processed right now.
Yeah.
And as soon as that's done, the CD part is going to kick in through ArgoCD.
So as we can see, our CI/CD pipeline is coming to a head. And there we go. In just over 2 minutes, we have built and pushed our new application to our Nexus. So our CI part of the CI/CD pipeline is now complete. So now we're back into ArgoCD. And we see the to-do app here. This is the app that contains our front end. We can actually go in and have a look at it, because you can see that the very helpful commit message that I made earlier has been detected. We can go and look at the information of the sources here. So we can actually, in the interface here, see that now we're using version 0.1.2 of the chart. And if all has gone well, our new app has then been deployed. And yes, our app has been updated successfully. Our CD part of the CI/CD pipeline has completed, and we are now creating awesome to-do lists.
While being under tremendous pressure, both the CI and the CD system didn't budge. It kept on working perfectly.
Yes.
Why? I think that comes as no surprise. We've cached all these type of artifacts. But I have one more question for you. So we talked about Docker. We've talked about Go. We've talked about NPM. What about Git and the Git repos as an artifact? What's your take on that?
So we have something very special in the works there. We have a separate, we're going to talk more about that later. But essentially, we've done very similar things as what we've done with the different artifacts, like Docker images, for example. We've done that, but with Git. And we've done a bit of an extra special integration there, where we do sort of a cache plus mirroring type of solution, which is really, really good for speeding up Git clones and Git fetches.
It was our intention to actually do some sort of Git integration and Git acceleration, but we quickly noticed that this is very much a webinar on its own. And that's exactly what we're going to do. So stay tuned for more content from Alve and myself, specifically on Git acceleration, which is especially useful when you're hitting GitHub rate limits or when you self-host your Git, right, Alve?
Yes, this is going to be very, very interesting for those who are running, a self-hosted Git repository. Git repositories are notoriously hard to scale horizontally. So we know that there are a lot of people out there with Git servers that are working real hard. And putting caches in front of that has turned out to be really beneficial for reducing the amount of work your central source of truth Git repository needs to make, in addition to speeding pipelines up even further.
Because remember, the start of any pipeline is usually a Git fetch or a Git clone, regular clones versus shallow clones. We'll talk all about that at the next webinar. And that's where we come to the end of this one. Thanks for watching this. I mean, we had all the bits and pieces in place. We really wanted to show it, and we're really proud of this solution. If you are a company that's struggling with CI/CD pipelines and you want to accelerate them, just reach out to us. I would just encourage you to go to our website, thevarnish-software.com. You'll find all the information you need. And if you want to reach out to us, please do so. We have a chat widget on the website that will quickly get you in touch with one of our people. So that's it. I want to thank you, ladies and gentlemen, for sitting through this one. And I want to thank you, Alve, for your help and all the hard work.
Thank you.